All right, how's it going, everybody? I am here making this video on Tuesday, April 20th, and today we're going to talk about section 3.7, the last section that we're going to cover in chapter 3. So our next video this week, as you can see above me right there, is going to be section 5.1. We're going to do 5 first, and then we're going to come back and hit 4, just because 5.1, in my opinion, falls directly after what we covered in chapter 3, whereas this stuff in chapter 4 is very closely associated, but is not like a direct. I mean, I think that section 5.1 could have just been section 3.8 instead, like it falls immediately after the stuff that we've been talking about here. So we're going to go chapter 5, then 4, then 6 is our kind of like last little perusal of some topics to wrap up this class here. So today, what we're going to do is we're going to classify, or we're going to summarize everything that we've seen on the last couple of weeks here, all of our classifications of the equilibria that exist at the origin for linear systems with constant coefficients. And again, we've said this a couple times now. That's a really, really specific thing that we've been talking about here. And so, what our goal is in chapters 4, 5, and 6 is to generalize the results that we've gotten here in chapter 3. Chapter 3 was super specific, but we got a lot of good information and we got it doing a pretty simple bit of math. We want to make this type of thing apply to more scenarios, and that's our goal in our next 3 chapters here. And again, we're only going to hit like a couple sections from each of these chapters, but we're going to get a really good idea of the things that are out there. So what we've kind of seen is that our eigenvalues are dictating everything about the behavior near the equilibrium. So what I'm thinking is to help us get a summary statement, let's just take our most generic possible linear system here and let's find its eigenvalues just in terms of A, B, and C and D, and let's see what we end up looking at here. So we know that to find our eigenvalues, we are always going to be looking at the determinant of A minus lambda I and setting it equal to 0. In this case, that gives me the determinant of a minus lambda b, negative b, a minus lambda b, c, d minus lambda should be equal to 0. This is giving me, and I'm going to do my usual flip here, lambda minus a, lambda minus d minus bc is equal to 0. I'm going to go ahead and expand this guy to get lambda squared. It looks like I have a negative a and a negative d on a lambda, so I'm going to say minus a plus d lambda, and then plus ad minus bc equals 0. So here's my characteristic polynomial, and I'm going to go ahead and throw this thing into the quadratic formula now to find my eigenvalues. We can see that according to our quadratic, we've got our a term, our b term, and our c term for our quadratic. My b term is negative a plus d, so negative b is positive a plus d. I'm going to keep it in parentheses here. Plus or minus the square root of b squared. Notice that this is a negative right here, so squaring kind of gets rid of that negative. So I'm going to say, I'm just going to call that just positive a plus d squared. Squaring would eliminate that negative right there, so I don't need to track that. Minus 4. There is no a term for the quadratic a right there. For a c is the ad minus bc here. And that's all divided by 2. So this is our eigenvalues here. So the important thing to me is that it turns out that there are 2 groupings of terms with our coefficients in here, the a plus d and the AD minus BC. And the thing that's convenient, especially for all you people that have already taken linear algebra out there, these are both already well-defined terms in terms of linear algebra, and we've been doing linear algebra to solve all these systems anyway. So what these 2 terms represent are the trace and the determinant of the matrix. We've been talking about the determinant. I know that you guys are all familiar with AD minus BC by now, but the trace is probably a new word to most of you that haven't taken linear algebra here. Trace is really, really easy. It's just the sum of the main diagonal of a square matrix. Main diagonal always top left to lower right. The off diagonal is the lower left to upper right up there. So our main diagonal, upper left to lower right, if you just add up all those numbers, that's what we call the trace. So you can clearly see here just a plus d is the trace of the matrix, and those are the terms that are popping out here. So the point is, let's go ahead and rewrite what we just came up with. We just came up with that phrase right there, a plus d plus or minus the square root of a plus d squared minus 4ad minus bc all over 2. And we can just rewrite this in terms of the trace and the determinant right there. It looks like a plus d is the trace, so we replace that twice. The determinant we'll call capital D, that's AD minus BC, and it looks like we're getting a much, much cleaner phrasing for what our eigenvalues are. The reason why this is a good move is because it's super easy for me in any of these cases here, super easy for me to compute the trace and the determinant in my head. All right, I can do that. No problem, mental math. I know that all of you guys are going to have no problem doing a little bit of addition, a little bit of multiplication and subtraction. No problem to do trace and determinant in my head. Then I can maybe think to myself about using the trace and the determinant to help me classify the behavior near the origin because I know what my eigenvalue formula is going to look like here. So now what I want to think about is we're going to be graphing things today. I mean, you can see it, the name of this section today is the trace determinant plane. What that means is we want to picture how do our classifications vary as the value of the trace and as the value of the determinant vary. And so maybe we can graph something in the trace as the horizontal axis, determinant as the vertical axis plane, and we can identify where we get certain types of classifications in that trace determinant plane. So let's start thinking about where some things are going to be here, right? Okay, I guess I want to leave that right there. I'll just leave this here. So first distinction that we want to identify is when do we get real versus complex eigenvalues? We know that that's the distinction between getting things like sources and, spirals and, wait a minute, spiral source, spiral sink. I'm swapping my words right there, and center. Versus our real eigenvalues, giving us just regular old sources and sinks as well as saddles, versus our repeated eigenvalues. We know that that's sort of like our transition between positives and negatives underneath the square root there. So what I'm thinking to myself is that these all seem to be well defined in terms of the trace and the determinant, because the trace squared minus 4 times the determinant is the discriminant in the quadratic formula here associated with the eigenvalues. So making this distinction, I think we should be able to recognize that graphing this t squared minus 4d being equal to 0 curve is going to be a helpful curve for us to identify. If you're above it, we know that we get one classification. If we're below it, we know we get another. If we're on it, we know we get a third type of classification here. And really, notice that over here, we really have 8 total classifications listed just by identifying what the value is of this discriminant based on the trace and the determinant. So what I'm going to go ahead and do is I'm going to take our trace squared minus 4 times the determinant. We know this is our discriminant, and we know that the discriminant discriminates between how many real solutions we're going to get. So by setting it equal to 0, we can find where that transition occurs. I'm going to add 4d to the other side, and I'm going to divide everything by 4 to get d equals 1/4 t squared. You should notice here I'm treating t as like our x variable and d as like our y variable. So our t-axis will be horizontal, our determinant axis will be vertical. Notice that we refer to this as the trace determinant plane, and we always say the input value first and the output value second, horizontal first, vertical second right there. So trace determinant plane. And so what I'm picturing for myself is this. It seems like in the trace determinant plane, we've got the trace axis, we've got the determinant axis, and it seems like there's going to be some parabola out there that's helping divide up our plane into classifications associated with the equilibria at the origin. Now, some things that I can see right away here, and I'm going to just rewrite our statement here. Lambda equals t plus or minus the square root of t squared minus 4d all over 2. So you should notice, one, that 2 does literally nothing for me to help classification. It's going to scale our eigenvalues up and down. We know that large eigenvalues are going to have stronger like sink and source type of action there, but it's not going to change necessarily the classification. What we're interested in is all this stuff up here in the numerator. So some things that I'm seeing. One, if we end up in the case here where we have, and maybe I kind of like to do this math with some inequality over here instead. For example, my question might be, where are the complex eigenvalues? Well, I can set up my t squared minus 4d is less than 0. And I can do the math to sort of solve for d here. T squared is less than 4d, and divide by 4, 1/4 t squared is less than d, or where d is greater than 1/4 t squared. So what that says to me is that our complex eigenvalues, these are our complex eigenvalues, are going to be above the parabola. Because the output value d is above the curve 1/4 t squared. So it looks like this is where we're getting our complex eigenvalues. Therefore, it must be that below the parabola is where we're getting our real eigenvalues. And further, I can see that where t squared equals 4d, where we're exactly on the parabola, that's where we're getting repeated eigenvalues. Right? So it looks like we're going to be able to fill out this plane with what our classifications are going to be based on just looking at our t squared minus 4d quantity right here, as well as you should notice this leading coefficient of t in our quadratic formula out here. T can either be positive or negative, and that should be indicating to us if we're doing things like sinking or sourcing, right? We know, for example, that if we have complex eigenvalues, that the real component, that'll be the trace term sitting out front right here, the real component is what tells us is it a spiral sink or a spiral source or a spiral center. And so I think just the sign of t should be enough to inform us of that right there. So, so let's go ahead and fill out a way better picture than this guy right here. This is just our first look at like real complex repeated roots from our quadratic formula. Let's actually name all 8 of these classifications in one good trace determinant plane right here by doing just a little bit of math here. So we're going to look at lambda equals trace plus or minus the square root of trace squared minus 4 times the determinant all over 2. All right. What I'm going to do is I'm going to make myself a nice big trace determinant plane out here. All right, and what I would like to do is I would like to place all of the classifications, all 8 of these classifications on their appropriate location in the trace determinant plane here. So let's kind of remind ourselves what we just saw. It seems like we know that we should have complex eigenvalues are above the parabola. And therefore, we know that these are associated with lambda equals a plus or minus bi, where this a is really the t plus or minus the square root of t squared minus 4d. So what I know is that the real component will tell us, are we sinking or are we sourcing? So it seems to me like if our t value is, so if we are above the parabola and our t value is positive, so we're on the right half, then we should have a spiral source. That's not how you write spiral. Let me try writing the word spiral again. Spiral source. Alternatively, if our trace is negative, then the real component is negative, and so we're going to get a spiral sink, and that's going to be on the left half above the parabola. And finally, what's the transition between spiral source and spiral sink? We should notice that if our trace is equal to 0 here, then we get 0 for our real component, which says don't do any growth or decay, just do the rotation. And so we're going to get a center if we are on the axis right here with t being equal to 0, right? So t greater than 0 is spiral source. T less than 0, spiral sink. T equal to 0 is going to be a center. So we can classify all of our complex eigenvalues in that way. Goodness. Okay, next grouping here. We know that real eigenvalues are below the parabola. We just checked that one out above. And so the next thing I'm seeing for the values that are below the parabola out here, what I'm sort of feeling out to myself is this. It feels to me like if my sources are going to be on the right-hand side, then I expect to continue seeing my sources on the right-hand side. One stupid thing I could do is you should notice that we should just be able to plug in a point. I can tell that the point 10, 1 is clearly going to be below this line right here, because if our trace is 10, then we're getting 100 minus 4. And that's 96. 96 is clearly going to be a positive value. And we said that when trace squared minus 4 determinant is going to be positive, we get those real eigenvalues right there. And so let's just take a look and see real quick. If we pick trace determinant equal to 10, 1, this is like just throwing in a test point into this region, right? That's like me testing that point right there. then we can see that we're going to get that lambda is equal to t plus or minus the square root of t squared minus 4d all over 2. And that's going to give me 10 plus or minus the square root of 100 minus 4 all over 2. Now, the important thing about this one is that you can see that this is the square root of a number slightly smaller than 100. And so what that means is that we're going to get two positive eigenvalues for this guy right here because the quantity, the square root quantity here was smaller than the 10 quantity right there. And therefore, when we add and subtract, even the subtraction version doesn't bring it down enough to make it negative. So it looks like we're getting a straight up source for this guy because we're getting two positive real eigenvalues. So it looks like this is just our source region over here. Conversely, I hope that you all can believe that we're going to get our sink region over here. And then we can see some other nice things. We also know that our, that's not all of our real eigenvalues though. What's our other thing that can happen over here? I don't know. Let's like kind of consider some other options that we're going to end up seeing here. Now, another thing that I might consider here is that so far I've really only labeled the top half of this guy here. What happens if our determinant is going to be negative? Here's what I'm saying if our determinant is negative. If our determinant is negative, then the square root of t squared minus 4d is actually larger than the square root of t squared, right? If d is negative, then we've actually added to the contribution that's underneath the square root. So it must be the case that when we do t plus or minus square root of t squared minus 4d, we get one positive and one negative, right? And so again, my logic argument for this one, if the determinant is negative, then t squared minus 4d, when you take the square root of it, is actually bigger than what t is. So when we do t plus that quantity, we get a positive, but when we do t minus that quantity, this quantity is bigger than t, so we're subtracting more than t has, so it's going to result in a negative right there. So we're getting one positive and one negative anytime the determinant is equal to 0. So it seems like anytime the determinant is less than 0, we're going to get saddles. So we're cruising here. We've covered our three complex scenarios. We've covered our three real scenarios with the source. The opposite was just the sink. Saddles are going to occur whenever the determinant is less than 0. So the only places we haven't talked about now are what's going on these lines right here. All right. And in particular, what I want to know about is what's happening on the t squared equals 4d line and what's happening on the t axis right here. So on the t-axis here, what we can see is happening is if we're on the t-axis, by definition, that means that d is 0, the determinant is equal to 0. And you should notice that if the determinant is 0, we're doing t plus or minus the square root of t squared. Well, that's clearly t plus or minus t squared. We're going to get the trace as one of our eigenvalues, and we're going to get 0 as our other eigenvalue right there. So I know that we're getting our eigenvalue of 0 scenario when we're on the t-axis right here. And so this was a whole line of equilibria. If we're on the sink side, we should be sinking towards that line of equilibria with all of our straight lines. And if we're on the source side, we should be all of our straight line solutions are pushing out perfectly away. So this would be a stable line of equilibria here. And this would be our unstable line of equilibria. Right, if we're on the t-axis. We know that saddles occur on the bottom half of the d-axis. Centers occur on the top half of the d-axis. So our very last classifications to state are what happens when we are on the parabola here. We've already seen what happens on the parabola right here. On the parabola is when we get our repeated roots. So we remember that what happened when we saw the repeated roots was we saw this was like the graph looked like it was trying to spiral, but it was blocked off by a single straight line solution. And so it was really like halfway between being like a sink and a spiral sink, or halfway between a source and a spiral source. We can literally visually see that graphical transition happening right here, that we are exactly transitioning between those two cases right here. So I think as our last one right here, um, on t squared minus 4d equals 0, repeated eigenvalues, and that was our degenerate source or sink. Only one straight line solution. And so it looks like we've got our degenerate sink is this guy. Oh, no, I'm not smart enough to do that. This is our degenerate sink. And this will be our degenerate source. When we are on those axes. So the point is, we have one graph that helps classify all of our possible outcomes associated with our linear systems of differential equations here. You can compute the trace and the determinant easily in your head. All you've got to do is think about the quantity t squared minus 4d and some signs on t, and you've got the whole dang thing right here. So being able to use the trace determinant plane is how we're able to super quickly, just doing a little bit of mental math, classify the behavior of any equilibria here. So let's go ahead and, oh, by the way, so unsurprisingly, the internet has 1,000 excellent pictures of this right here. So you should stop for a minute and stare at this. I only have one complaint about this very nice diagram right here. And that is that they call this the determinant trace plane, but I feel like that's backwards labeling. We always labeled the horizontal axis as our first value and our vertical axis as the second value when we're stating ordered pairs. They should definitely call this the trace determinant plane right here. But you can see that they're getting exactly the results that we got. Above the parabola is all of our complex stuff. Underneath the parabola is all of our real stuff. Our negative trace values lead us to sink type behavior. Our positive trace values lead us to our source type behavior. The entire bottom half is all of our saddles. The only thing also that's slightly confusing about this is that I feel like they label these things like the line of stable and unstable fixed points right here. Look like they're labeled on the bottom half, but there's really got these little arrows that are pointing at the axis lines right there. And give me just 1 second real quick. I just need to step away real briefly. All right. So, much nicer. Oh, what'd you do? Oh no, oh no. Keep it together, word. Keep it together, word. There we go. So, our much nicer diagram right here, and I just Googled for this. So this is a good thing for you to keep available for yourself so that you can reference your diagram, make those quick classifications based on just doing a little bit of mental math. So let's go ahead and do some examples of this. I want to classify the behavior near the origin for each of the following coefficient matrices, and I'm just going to remember for myself, I just keep on writing my same statement here. Trace plus or minus the square root of trace squared minus 4 times the determinant, all divided by 2. That's how we're determining our eigenvalues. Our eigenvalues are determining our classification. So let's go ahead and do our math real quick right here. So trace is the sum of the main diagonal. It's 4. Our determinant is the down diagonal product minus the up diagonal product. We can see we're going to get 4 minus 3 is going to be 1. So when I look for my classification here, I'm going to go ahead and do my trace squared minus 4 times the determinant. That's going to be equal to 16 minus 4. That's positive. I don't care that it's 12. I really don't. I care that it's positive. I'm looking for the sign of t squared minus 4d. This is going to tell me that it is real eigenvalues. Then what I can see is I know that I'm getting my real eigenvalues right here, and that my trace is going to be positive, and therefore we must be a source. All right, so there was my kind of like progression of thought on that guy right there. Find trace and determinant, compute t squared minus 4d, determine if it's positive, negative, or zero. If it's positive, they're real. If it's negative, they're complex. If it's zero, it's repeated roots. Then I just need to know the signs of t and d to make my next step down classification. All right. Same thing with this guy here. So let's keep on doing these, see if we can just rifle right through them here. Trace looks like it's 1. Determinant, negative 12 minus negative 14 should be positive 2. T squared minus 4d is going to be 1 minus 8 is negative 7. I really just care that it's less than 0. So we're getting complex eigenvalues. For the complex eigenvalues, I know that I'm just interested in knowing, was the trace positive or negative right there? Are we spiraling in or spiraling out? We've got a positive trace, so this must be a spiral source. And our last example down here, it looks like my trace is negative 4. It looks like my determinant is negative 5 minus negative 9, which is going to just be 4. I'm going to do t squared minus 4d, and I'm going to see if that's 16 minus 16, which is equal to 0. That says to me we get repeated roots. So let's remind ourselves of this scenario here. This says to me I am on the parabola right here. So if I want to know, are we a degenerate sink or a degenerate source, we again just need to look at our t value. Are we on the left or right half of the graph? It seems like our trace is negative, and so we should be a degenerate sink. So real quick classifications right here. We're classifying the behavior near the origin of a system of differential equations by like barely doing anything at all. I'm just taking very basic use of some quantities in linear algebra, very basic use of the quadratic formula, and just applying them to a picture of the trace determinant plane and ending up with classifications of any of our possible outcomes near the origin right there. So this is really cool that we can do this very quickly. So you just got to kind of remember this diagram right here and remember our basic phrasing for our eigenvalues right here. Trace plus or minus the square root of trace squared minus 4d. Who even cares about the divided by 2 right there, unless I say to you literally what are the eigenvalues? That 2 doesn't ever affect our classifications. So you can see we can do some real quick work right here. So one of the things I am going to ask you to do this week is this. When I show my work, like what you're seeing on the page right here, I feel like it's very rare that I see students write their work the same way as I'm writing it right here. So one of the things I'm going to ask you to do for your homework this week is for you to write like a tree diagram of how you make your decisions as you're doing your computation. So the very, very top of the tree, your root of your tree is going to say compute, trace, and determinant. And then I want to know from you, what are you checking? What's your systematic way of going about determining, from knowing trace and determinant, what are like the checks that you're doing? Oh, I saw it's real, so I should check this. Oh, I saw it's complex, so I should check this. Oh, I saw it was like, go on down the line right there and sort of make your decision tree like a visual chart that can help you classify these things so that you can just like run your finger along the tree and say, oh, it's this right here. So that'll be one of your homework things, is saying to yourself, most people don't write their work like I just wrote mine right here. I want to know how you think about this. What's your like step-by-step process to walk through this here? So, well, here's the deal. This seems pretty useful. When is this not as helpful as we want? Fortunately, there are only 2 relatively small situations in which we get a little bit stuck with this guy right here. And neither of them are a huge deal. One of them I'm basically not worried about. The other one, we just got to do a little bit of math to worry about. The first scenario of when we might get a little bit of confusion right here is that when we get repeated eigenvalues, we can't tell if there's one eigenvector, a degenerate sink or source, or if there's infinite eigenvectors, like we saw with our star sink or star source. Remember that when we have this sort of like symmetric matrix right there, stop underlining things in red that you don't have a problem with, Microsoft Word. Thank you. That this matrices of this form right here will have that every single eigenvector, or sorry, every single vector is an eigenvector. Whereas over here, we're only going to get one special vector is going to be an eigenvector. So you can go ahead and do the math. I'm not going to do it because I've done both of these right here. But both of these will have the case that t squared minus 4d is equal to 0. And by the way, I guess I should do, that's what I should do right here. Is let's actually compute t squared minus 4d right here and see that my trace is negative 4. My determinant is negative 5 minus negative 9, which is 4. And so t squared minus 4d is 16 minus 16, which is equal to 0. But there's only one eigenvector that's going to be associated with this guy. On the other hand, over here, my trace is 0, and my determinant is oh, sorry, my trace, I'm like, wait, that doesn't make any sense. My trace is 8, and my determinant is 16, and we're getting t squared minus 4d is t squared is 64 minus 64 is 0, but here we're going to get an infinite number of eigenvectors. So the important thing to watch out for there is if you do get that you have a t squared minus 4d is equal to 0, you're actually not quite done doing the classification. However, the reason I'm less worried about this one is because this is always visually identifiable. When you get the zeros on the off diagonal and the same number on the main diagonal, that's going to be what it looks like every time you're going to get the infinite eigenvectors. So, it's a little bit more difficult to get like tricked in this situation right here. Let's go ahead and look at one that's slightly more interesting right here. If we end up finding that t squared minus 4d is less than 0, we're going to get complex eigenvalues. But what we can't, and we can tell if it's going to be a sink or a source or a center by the sign of t, right? If t is negative, we get a spiral sink. If t is positive, we get a spiral source. If t is 0, we get a center, no growth or decay. The problem is that we can't tell what direction we're rotating. It could be a spiral sink, but you could have spiral sinks rotating clockwise. You could have spiral sinks rotating counterclockwise. So let's real briefly look and see what our scenario is right here. I think I should probably bump this guy down right here. So what are we going to get here for our A and our B matrix? I'm seeing here that my trace is 0 and that my determinant is 0 minus negative 1 for 1. So t squared minus 4d is going to be 0 minus 4, which is less than 0, so we're complex. Then I'm seeing here that our trace is 0, so we're going to get a center. Over here, I'm seeing that our trace is 0, and that our determinant is going to be 0 minus negative 1, so it's positive 1. So t squared minus 4d is 0 minus 4, which is less than 0, so we're complex. And I go to look at my trace, and my trace is equal to 0, so we are a center. Again, so they're both centers. That's what I'm seeing right here. But the question is, what direction are they rotating? To check the direction of rotation, I can just check the vector at any one point. So what I'm going to do here is I'm going to check out a vector, and I'm just like kind of picking a location out in phase space out there. I know that we should be a center. I know that we should be getting a graph of something that just has cyclic, repeating stuff, but I don't know if we're going this way or if we're going this way. I'm thinking circles. I'm thinking ellipses out there, stuff like that. So let's go ahead and multiply our A matrix times a vector out in space, right? So I'm just checking. I guess I picked the point 1, 1. So what I'm seeing here is if I check out what's going on, what is our rate of change at 1, 1? When I do this matrix math right here, right? This is my XY point right there. This is my A matrix. It looks like I'm going to get 0 times 1 is 0. 1 times 1 is 1. Negative 1 times 1 is negative 1, and 0 times 1 is 0, so I'm getting a 1, negative 1 right there. And so what that says to me is that this is the vector that looks like starting here, and it goes 1 unit to the right and 1 unit down. So I know that I'm getting a vector that looks like this at the location 1, 1. I know that I get the vector 1, -1 right there. So wherever we're looking out here, I know that I'm getting that vector. So this seems to suggest to me that we must be doing some clockwise rotation. On the other hand, over here, I could look at my B matrix of 0, -1, 1, 0, and I can also check out what's going on at the location 1, 1 on this graph right here. Remember, this is my xy point right here, and I'm saying, what's the direction of motion at that xy point? Well, if we do our same math right here, 0 times 1 is 0, -1 times 1 is -1. 1 times 1 is 1, the other one goes to 0, so we're getting -1, 1. And so you should notice here, this says at the point 1, 1, what type of motion should we be experiencing? We should be going to the left by 1 and up 1. So I'm seeing here, we're getting this vector right here from the point 1, 1. Why did I just write 1, 0 right there if I'm saying 1, 1 and thinking 1, 1? Come on, brain. And therefore, I can see here when we go to the location 1, 1 in space, we should be going to the left one and up one as our direction of motion from that point in space right there. So it seems to me like this guy is certainly rotating counterclockwise. So if we're ever looking for direction of motion for a spiral or a center, you can always just literally pick any point in the plane. Figure out what direction your vector is pointing you in at that direction in the plane. And from there, you should be able to pretty easily determine what direction you are rotating right there. I even think I picked a slightly dumb point right there, 1, 1. Why I didn't pick 1, 0 or 0, 1, I don't know. I think that would have made our math even easier right there. But recognize if you get a spiral sink, a spiral source, or a center, you don't have information from our eigenvalues if the rotation is clockwise or counterclockwise. So you've still got to do a tiny smidge of math, but it ultimately amounts to you picking literally any ordered pair in the xy plane out there, hitting it with your coefficient matrix. You're essentially just computing dx dt and dy dt, and from that getting like the slope of a vector in your phase diagram that's out here. And remember, when we go to Bluffton and see these things right here, they're plotting a picture that has like 200 arrows on the page. We just wanted to produce one of them, and that's enough for me to know the direction of rotation if we do have one of our rotational classifications there. All right. So there we go. So there's our drawbacks page right there. Pretty dang easy stuff. The distinction when we get t squared minus 4d is equal to 0, you get this very easy to identify infinite eigenvector situation distinct from the one eigenvector situation. When we get rotation, we never know what direction we're rotating based just on the eigenvalues. So we've always got to do like just try a point real quick is all you got to do right there. Pretty quick and easy single matrix multiplication right there, and we can judge the direction of rotation counterwise. I better change that. That was man. That's what happens when I write and talk at the same time here. Counterclockwise. Okay, there we go. A little less embarrassing right there. All right, so next topic here. So we've just got these next two ideas right here, and we'll wrap it up. The trace determinant plane for harmonic oscillators. So next thing I'll say here, let me maybe get that going on. There we go. Trace determinant plane for harmonic oscillators. What we know is that we've been looking at we've been looking at linear systems of differential equations in general. But one of our most important cases is referencing the fact that our second order differential equations describing harmonic oscillators seem to be pretty closely tied to our linear systems of differential equations here. So one thing that we might naturally ask ourselves is, in the trace determinant plane, what might come up if we're talking about a harmonic oscillator? And here's the deal. Harmonic oscillators have to meet real-world physical restrictions. Things like mass needs to be positive, stuff like that. And that really means things like the signs on our parameters are kind of predetermined for us. You can't have like literally any choices of A, B, C, and D out there, and therefore I don't expect to have any possible arrangement of T and D in my trace determinant plane either. So not all classifications are going to occur associated with harmonic oscillators. And you should stop and ask yourself for a minute. When we're talking about harmonic oscillators, when we're talking about things like a mass on a spring, my question for you is, out of all the classifications that you see here, which ones do you think represent realistic possibilities for what could happen when you place a mass on a spring and slide it back and forth on like a countertop? Out of all the ones that are here, which ones could be the description of the motion associated with that mass on a spring? Let's go take a look mathematically down here. So here's our statements that we know. We're going to start from our Newton's second law of motion, force equals mass times acceleration. We know that acceleration is really the second derivative of position. We also know that our spring force is going to oppose position. Springs oppose position. If you're past your point of rest, you're going to get pulled back towards it. If you've compressed the spring, it's going to push you back out. Position is what judges the direction of motion for the spring. We know that our damping force is dependent on velocity. The faster you're going, the more friction force you're going to experience, and that is a resistive force right there. So the things that I know that are really important here are parameters of M, K, and B, that we know that our mass is strictly positive. We know that it's possible to have no damping in a system. It could be that B is 0, but I know that my spring force here can't be 0 or it's not a spring at all. So we're going to get that K is positive, and we're going to get that B is greater than or equal to 0, because you could have no damping in like some ideal setting in a system right there. So what I'm going to do is I'm going to write this second order differential equation. Then we've got that force equals mx double prime. The sum of our forces is the spring force plus the damping force. That's our negative kx minus bx prime equals mx double prime. And this is what led us to our system of differential equations here. So I'm going to go ahead and I'm going to divide everything by m. Come on, come on, come on. Yeah, that's fine. And then that's where we make our conversion into a system. We say the derivative of position over time is velocity. And the derivative of velocity over time is exactly acceleration, is exactly this expression that we're looking at right here. And so it looks to me like I've got my negative k over mx minus b over mx prime. And that leads me to my A matrix here being 0, 1, negative k over m, and negative b over m. And the thing that I'm remembering for myself right here is that I know what signs are going to be tied to the k's and the b's and the m's right here. So it seems like now I could compute my trace and my determinant associated with this very general oscillator coefficient matrix right here. Seems like my trace is negative b over m, and it seems like my determinant here is 0 minus negative k over m, which is just k over m. So it looks like my trace is always negative. Now, b could be equal to 0. It looks like my determinant is always a guaranteed positive divided by always a guaranteed positive. It's going to be always positive. So this says to me that we only ever get classifications in the second quadrant of the TD plane, including the d-axis, right? Because t equals 0 is possible right there. T equals 0 is possible if there's no damping. So we should get that little piece of the d-axis that's right there. And so what this is therefore going to look like to me is to say we're really only interested in this second quadrant stuff that's over here when we're looking at harmonic oscillators. So what are all the possible classifications? We could have a spiral sink We know that that's possible with a harmonic. That's exactly what I typically picture with the mass on a spring, is it bouncing back and forth till it comes to rest. Technically, because we could have no damping, we could have a center. That's our d-axis right there. There's our negative t-axis over here. It seems like we're only in the upper left part, so there's no saddles that can ever occur out here. It looks like we could just get a straight up sink. We could just decay towards the origin, or we could get a degenerate sink. So these are the only classification settings that are associated with our harmonic oscillators out here. And so what happens to any oscillator? It's either undamped, that's where we get our periodic orbits, it's our center, or it's damped. Those are the two possible cases. Either it has damping or it doesn't. If it's damped, then that's where we get that it decays to zero, or decays to, I'll just say decays to zero, decays back to rest. And this is our sink, our spiral sink, and our degenerate sink. Right? We're never going to have a mass on a spring where it like blows up over time and starts doing all this crazy stuff, right? We can't possibly have source type behavior when we're talking about a mass on a spring. So you should just recognize that our harmonic oscillators are always tied to our scenarios where everything either goes to zero, so all of our possible sink type classifications, or in an ideal setting, we could have a center where nothing decays down to the origin and we just maintain these periodic orbits forever out there. All right? So, last topic of the day for our summary section right here is the critical loci, as the book likes to refer to them as. And what they really mean, I feel like this is like a weird place to use like some fancy word, loci. I guess loci are locations, the critical locations. I want to remind you that we referenced this word critical here previously when we talked about these locations in the plane, in that the word critical in math usually means a transition point. Our critical values in Calc 1 are where our derivative changes sign, right? Similarly here, our critical loci are where our trace or determinant are changing sign, or where we're jumping over that parabola, right? So the most important locations in the TD plane are the t-axis, the d-axis, and the t squared minus 4d curve, right? When we very first drew our first picture of this guy right here, I only drew those three curves out there and said, yeah, we get real complex and repeated eigenvalues at these locations out there, right? So the two axes in the curve are clearly our most important locations, and our question is, when are we going to cross those things? So as the parameters, as the four values A, B, C, D within our A matrix vary, it might cause us to cross one of the three lines or curves, the two axes in the curve out there, which would cause us to experience extreme change in the overall behavior of the system. We know that we already have a name for this type of thing. When a small change in parameter leads to a broad categorical change in behavior, that's referred to as a bifurcation. And so with the trace determinant plane, we're interested in doing a little bit of bifurcation analysis associated with unknown parameters in our coefficient matrix. So let's go ahead and take a look at an example of this right here. I really, really like this. I feel like bifurcations are hard when you first see them, and then they're easy. And I feel like classifying our linear systems is hard at first, and then it gets easier. And this is a nice like tie together of things that sort of used to be hard that now are easier right here. So what I want to know is, what are all of the possible classifications of the behavior near the origin of this linear system of differential equations? And I want to know what values of A cause us to experience those classifications, right? So determine all possible classifications of the equilibrium at the origin and the A values that those are associated with. Identify the bifurcation values of A. What value of A represents a transition between two cases, right? So what I'm going to do is I'm going to do the same math that we've been doing. I'm going to say, okay, what's my trace? Well, let's add up the main diagonal. It should be -2. What's my determinant? Well, I'm going to do 0 minus -2a, so it's going to be a positive 2a. So in my trace determinant plane, I don't know necessarily what my determinant is, but I know that my trace is going to be at -2. So I think in my trace determinant plane over here, what I can do is this. I can say, here's my TD plane, trace and determinant. What I know is that I've got a trace. Let me get a better color right here. I know, or sorry, I've got a trace of -2. My determinant is unknown. So here is my line that represents the trace of -2. That line turned into a curve. Let's try that again. Now, what it seems to me is happening here is it seems to me like given some values for D, we might end up below the t-axis. Down here, there's saddles. There could be a special value of D, like A being 0, that could cause us to be on the t-axis. That's going to give us our line of equilibria. It looks like there should be some small value span of values for A that result in D giving us a value that's between the axis and the curve. These should give us sinks. It seems like there's going to be one special value for A that's going to cause us to get a D value that puts us right on the parabola. That's going to be our degenerate sinks. And it seems like then for all values of A beyond that value, our A value is going to be large enough to cause our D value to be large enough that we're always going to be within the parabola and we're going to be getting some spiral sinks out there. So what I feel like I'm seeing here is I feel like I'm seeing that there's a special value and a special value right there. I think I know what the classifications are going to be. I think I know this is a saddle. I think I know this is a sink. I think I know that this is a spiral sink. I know that this is a degenerate sink. Degenerate sink, it's trying to sink like a spiral, but it can't quite. And I know that this one right here is going to be a stable line of equilibria. All right, that's where we get a whole line of equilibria because we got a lambda being equal to 0 in that case right there. So my question is, what are the A values that cause this to happen? That's what I'm not quite sure about yet. Well, one of them is pretty easy right here. I can see that I'm interested in knowing when is D equal to 0 and when are we going to hit the parabola here. So let's solve those. So let's go ahead and solve for what the two values of A are that are going to cause this to happen. So when are we going to hit D equals 0? Well, that one's super, super easy. So if A is 0 right here, then our determinant value is going to be 0, and we're going to be right on the t-axis. That's associated with this point that's sitting right here. And that's where we had that stable line of equilibria. So I now know that this is tied to my A equals 0 right there. The other thing that we were interested in is where is t squared minus 4d equal to 0? That's when we're on the parabola right there. Well, I know that my d value is 2a. So this is going to give me t squared minus 8a is equal to 0. And my question is, what value of a is going to make that guy happen for us here? Oh, and I know my trace here as well, actually. So sorry, I was like, wait a minute, how am I solving for this right here? Let me go ahead and actually throw the two values that we know. We know that trace is -2, so I'm going to do my goodness, I can't write. So I'm going to do a -2 squared minus 4 times 2a equals 0. 4 minus 8a equals 0. And it looks like a is going to have to be 1/2. So it looks like these are my bifurcation values for A because they are the places where we transition from one classification to the next. So that's one part of my answer right here. And it looks like I can now list all of my classifications. So I'm basically just going to redraw this, but I'm going to be a little bit better about my listings right here. It seems like we're going to get A equals 0 and A equals a half. So A equals 0 is here. A equals 1/2 is here. And remember that I'm just drawing this line relative to its position in the trace determinant plane down here. So I think I can do my kind of like best classification here by just kind of listing what the interval is next to it right there. So this is a stable line of equilibria for A equal to 0. Again, back up in my trace determinant plane, our chunk in between the two right here, this is when we're getting real valued solutions. We're on the left-hand side, so that's just a straight up sinc for A being between 0 and 1/2. And those are strictly less thans right there. I've got the equal to's covered in other cases. It looks like the next point of interest, our other bifurcation, was when A is equal to 1/2 is when we're going to hit the parabola right there. That's going to be our degenerate sinc. That's when it's trying to be a spiral, but it can't because there's one straight line solution that's blocking it from spiraling. So our degenerate sinc is occurring when A equals 1/2. And then finally, above the degenerate sinc is when we're within the parabola. That's our complex region. It's on the left-hand side, so that must be our spiral sinc region right there. So a spiral sinc should be associated with A being greater than 1/2 right there. All right, so we've found the bifurcation values and we have fully classified all possible behavior. There's 5 different classifications that this system could experience depending on the choice of A, and we've determined all 5 classifications and the A values that cause us to experience those. I really like these problems right here. This really does tie together lots of good things: bifurcation values, eigenvalues, trace determinant plane, classifications, all these kind of good ideas. None of the math right here is really hard. This is just, can you read a picture really well and understand how to do some kind of relatively basic algebra, but we got a lot of parameters floating around out here. So these aren't like the easiest problems. These are problems that are hard until they're easy, and then once you're done, you're like, oh, none of that math is bad right there. So you'll see a couple of these that are really good in the homework. I like these guys quite a bit. This is admittedly a slightly easier example here. I will hit you guys with one where there is more than one of the slots in our A matrix has a parameter value in it rather than a known constant like 0 or -2 here. But the idea is still the same. You should draw the line that you get in the trace determinant plane as determined by the trace and determinant that you're given. You should notice it's even possible for the trace to have A in it as well. In that case, it's really just like I gave parametric equations right here for the trace and the determinant. In fact, to that end, to wrap up the video right now, what I want to do is I want to show you what this looks like in Desmos here, that you can do this for yourself. Over here in Desmos, I've graphed the trace determinant plane. That's our equation here. This is my t squared minus 4d equals 0. And I literally graphed parametrically the point -2, 2a. Our trace was -2. Our determinant was 2a. And so that allowed me to place a point on what is effectively a trace determinant plane right here and slide it around and see where things are happening. I also plotted this because otherwise it wouldn't show me the whole line that thing is moving on. So I just said trace is equal to -2 and it plotted the vertical line. But you can even see the things that we concluded, which is that when A is 0 is when we're right on the line. When A is equal to 1/2 is when we're on the parabola. Above 1/2 is when we're in the complex region. Between 0 and 1/2 is the real region. Below 0 is when we're in the saddle region down there. I should say real region. Real is everything below the parabola. Real but sinc region. And then we get our saddles down here. So like maybe this is helpful. Again, it might end up being that you get something that looks like, 2a, I don't know, squared or something like that, then you've got to do a little bit more, maybe thinking about where you're maybe. So this guy right here, I don't think that's like the most outrageous thing that I've ever done right there. And in fact, I think I could do something like a -2t. Is it going to let me do this? -2t squared 2t. Oh my gosh, are you kidding me, Desmos? Is this a joke right now? How many times do you think I want to be doing superscripts and subscripts? Goodness gracious. I don't think this is any sort of unbelievable diagram right here where you could end up with your trace being negative 2t squared and your determinant being 2t. And then you would again need to identify that you're going to get a bifurcation happening here when it looks like t is equal to 0. And you're going to get a bifurcation out here in your parameter a is equal to 0. And another bifurcation out here at, I don't know, is that 1.25 maybe, something like that. You would be able to solve for that value and say, over here we're getting sinks. Here we're getting degenerate sinks. Here I'm getting spiral sinks. Here I'm getting that uniform motion in the plane. And down here we're getting saddles, right? And again, you could make that type of distinction out there in the trace determinant plane. So use Desmos to help you if you want, but my big advice to you is when you're playing these classification games with an unknown parameter out here, it's really, really important that you draw the line that is technically the parametric equations for your trace versus your determinant in terms of the parameter A. So that way you can physically see where these transitions are occurring. Trying to do this problem without drawing a picture is kind of a pain because then you have to like literally do the math for all of your classifications rather than just see it in the picture right here. So that's going to wrap it up for our trace determinant plane. What we're going to do in the next video is section 5.1, not 4.1. We'll do 4.1 next week. 5.1 is when we're going to say, okay, so we just spent like a month classifying equilibrium at the origin for linear systems with constant coefficients. That's super, super, super specific. We want to start breaking away from that and saying things like, what if our system's not linear? What should we do? What if we have equilibrium not at the origin? What should we do? Both of those topics are going to be handled in the next video. In chapters 4 and in chapter 6, we're going to say, all right, so maybe we get into situations where we can't just do linear algebra anymore. What other types of calculus operations should we be doing to solve other second order systems? So the reason I'm doing 5 next and not 4 is because 5 still deals with systems of differential equations, whereas chapter 4 and chapter 6 deal more specifically with second order differential equations. So I feel like 4 goes with 6 better, and I feel like 3 goes with 5 better. So that's just why we're doing like a little bit jumpy out of order here, but it's nothing too crazy. I think you guys will agree that when we cover 5.1, it just feels like a very natural extension of chapter 3 ideas. So I will see you guys in the next video for 5.1. Have a good one.